Hi, welcome everyone to the multi-institutional AGN seminar series. My name is Vivian Yu, and I'm an astronomer based in UC Irvine and a co-organizer of this seminar series. And I'm not late today. So today I have the pleasure to introduce Dr. Hanae Inami as a speaker. After getting her bachelor's degree from Meiji University, Hanae went on to study at the Graduate University for Advanced Studies, where she majored in space science. She was also a visiting graduate student at Caltech IPAC, where she started her adventure into the land of dusty infrared galaxies, and I had the luck of collaborating with her. She went on to do her postdoc at what used to be called the NOAO, for those of you who remember, and then the French National Center for Scientific Research. In 2019, she joined the Hiroshima Astrophysical Science Center as an assistant professor and spends her day working on the enigmas of space. And today, Hanae will be telling us about AGN or starbursts in JWST 96. So please take it away.
Thank you, Vivian. That's really nice introduction. Thank you. And I feel very lucky that I have this opportunity to talk about our recent works based on JWST data. So again, I'm Hanae Inami from Hiroshima University, and this work is based on the project I'm going to mention later in the talk, GOALS. And I will be talking about this galaxy showing the background, very beautiful, called JWST 96. So JWST 96 is, a minute, I cannot change the screen. Let me start again. Okay, is luminous infrared galaxies. And let me see if and we often call it just LIRG. And the definition of the LIRGs is this galaxies with the total infrared luminosity higher than 10 to the 11 solar luminosities. And they emit most of their energy in infrared, as you can see from this huge number. And the reason they are so bright in infrared is it has enhanced star formation or have a very high fraction of AGN compared to normal galaxies and hidden in the dust. An interesting thing about local luminous infrared galaxies is it covers very wide range of merger stage. So you can see in the background of this slides, we have something galaxies look like single spiral, some are the pair, and some are in the middle of merger and the final collapsion. So they are a nice data set for us to study the merger-induced activities in galaxies. They are relatively rare in the local universe, but interesting thing is they are the dominant population at high redshift. So I'm showing this one. This slide is this plot is taken from McNally et al. 2013, showing the infrared luminosity density in the universe from redshift 0 to 2 based on the Herschel data. And at redshift 0, you can see the LIRGs and ULIRGs, which is ULIRGs is even more luminous, 10 to the 12, and solar luminosity higher. Their luminosity density is not very high, but by redshift 1 or 2, they are the dominant population in generating infrared luminosity in the universe. So since they are the very bright sources that have enhanced star formation and AGN, so they are ideal laboratory for detailed study of these kind of extreme phenomena. And also they are one of the ideal local analogs to study distant galaxies. So in order to make these happen, GOALS project, Great Observatories All Sky LIRG Survey, have conducted a survey with a multi-wavelength observations on 202 luminous infrared galaxies in the local universe. And our samples are flux emitter sample and taken from the IRIS revised bright galaxy sample. So the multi-wavelength data are taken from both space and ground, Spitzer, Herschel, HST Chandra, and many, and so on. And this time we have an exciting addition from JWST EIS program. We took 4 objects and the observing time is roughly 38 hours. And this EIS program 1328, the title is a JWST study of the starburst AGN connection emerging luminous infrared galaxies. Based on this, in this project, we try to study the phenomena of star formation, black hole glows, and feedback in 4 targets, and they are all merging infrared luminous galaxies. So we try to answer following questions. How do stars form and black hole grow in merging galaxies? How do they impact the ambient ISM? What are the implications for the models of field and feedback? In order to do this, we have 4 observing modes in near-infrared, near-cam, near-spec IFU, and then 2 near-infrared modes we use, near-cam and for imaging, near-spec for IFU spectroscopy, and mirror imaging and IFU in near-infrared. The co-PIs are LIRGs and RN events, and we have 21 co-Is and 8 science collaborators in 8 countries and 18 institutes. So the 4 targets we are targeting with this program are these 4. So let's start with top left, IIZw096. This is a late stage merger. You can see there are two nuclei, but maybe it's a bit hard to see the second one because it's buried in the dust. And that's also speculated it may have an AGN. And both nuclei have very strong outflows, and lots of short gas also has been detected. And you can see all this the point sources look sensing. Those are the superstar clusters. This is one of the targets we have has a rich number of star clusters. And then NGC 70469. This is actually a pair galaxy. The second one is outside of this box, which is 26 kiloparsecs away. And the nucleus of this target is safer. And around here, I hope you can see my cursor. Around here, the AGN it has a star formation ring, and it's known to have bimodal stellar populations. And the nucleus also have known to have a biconical ionized outflows. And VV114, again, is a merging pair. And interesting thing is the eastern part, that is a dominant source of infrared emission. But the western one, that one dominates UV and optical. And in the interface of this merger, it's known to have merger-induced shocks as well. And the nucleus of the eastern source may have a barrier AGN. And to the kinetics, this is what we're going to talk about today. It's a late stage merger. It's a luminous mergers, and most of the infrared emission is coming from the compact region around here, which I'm going to follow up detailing later. And this source is actually completely buried in the dust, so we need the infrared data to actually see them. Okay. So based on these 4 sources, we carefully choose this to cover most of the typical phenomena in local luminous infrared galaxies. So looking at those 4 sources, we'll study nuclear star formation by measuring the star formation and size and so on, and we'll study feedback. And because we have IFU data, so we can actually finally map the extent and impact of feedback around the nucleus. And of course, there are some sources we know it's speculated to have AGN, so we're going to try to find them, to finally identify their existence and study the gas accretion around them. And in stellar clusters, thanks to very high resolution of JWST, finally we'll be able to study if there's any dust-buried superstar clusters and how they relate to merger. So so I mentioned briefly about our observations, but here is a little more detail. So for IFU spectroscopy, we will target it at nuclei. And for MIRI, we cover 5 to 29 micron, and near spec will be from 1 to 1 to 5 micron. And imaging for MIRI, we cover 3 filters, 5.6 micron, 7.7, and 15. And near-cam is 1.5, 2.0, and 4.4 for the broadband filters, and 3.3 for medium band filters. And we also take sub-array imaging because you can imagine we have very bright nuclei and they can saturate the full array. So we take the subarray imaging to recover non-saturated image of the bright nuclei. So these four sources, they show different spectra that in the data we have taken in the past. So here are the spectra taken from Akari and Spitzer. So Akari cover 2.5 to 5 micron, and 5 micron to 38 spectra are from Spitzer. And this color of the spectra correspond to the box I draw around each target. And you can see some of them have a stronger pH, some don't, and some have deeper silicate absorptions, and some sources have much redder continuum than others. So, and this was only in one dimension because of Akari and Spitzer, but now, as you can see, this box, that is the rough field view range of the IFU data of MIRI. We will be able to actually resolve this nuclei region and then have the 3D view of these sources. So the exciting thing is JWST will cover the same range that we have taken also with Akari and Spitzer, with 50 times higher sensitivity and 10 times higher spatial resolution and 5 times higher spectral resolution power, plus it is IFU. And our data, they have been actually coming in since July, and we don't have all the data yet, but we have 7 papers that are already submitted or accepted. So for 2086, there's a paper that we're going to talk about today. And for NGC 7469, we have 4 papers, 3 are based on spectra and 1 is imaging. And for VV114, we have 2 imaging papers. And NGC 3256 data will be coming in December. So all of these papers are on archive. So if you search by Google goals JWST on archive, you should be able to find all of them very easily. All right, so I want to go a bit deeper to talk about 2086. Today is our main target. So this source at the spectra look is showing the orange here. So far from the spectra we know is you have relatively red infrared continuum emission, but we haven't had any coronal line emission detected with Spitzer data. And looking at all this PAH emission, polycyclic aromatic carbon, people often use this for star formation indicator. They are intermediate. So based on the data we have in the past, we so far cannot tell if this source is bright infrared because of AGN or because of starburst. But before going into JWST data, let me give you a little bit of background for this 2086, this target. So this 2086 is at redshift 0.036, and it was infrared luminosity has been measured by IRAS in the past. But later on, Goddard et al. 1997 have done the follow-up observation on using the ground-based H and K-band observations of this source, and discovered very rare sources. They call them C and D outside here. So it's outside of the main parts of the galaxy. So let's make this target very unique and interesting. And we then follow up this target with Spitzer and HST. So I would like to show you what HST image look like compared with this Goddard et al. So the very red region, as you can see here, this is the region that Goddard et al. Found. And it's very, these regions, you don't see it in B and I band, but only started very much, but in H band, you can see it's really very bright. So the Spitzer follow-up observation also actually show this. So these are the 4 band from IRAC, from 3.6 micron, 4.5, 5.8, and 8.0 micron. You can see C and D are the brightest, but it gets even brighter with the wavelengths. And at mid-infrared, 24 micron, 70 micron, we can see it is almost like it's a point source is dominating the emission. And if we estimate how much, assuming it's the point source dominating the emission here, 70% of the emission will be coming from this single source. And at 70 micron, that can be go up to 90%. The far infrared emission is dominated by a single source. So then we will be curious which source as dominating is producing all this infrared flux. And here, if I overlap the Spitzer 24 micron contours on far UV, B band, I band, H band images is on the right-hand side, we can try to identify which source is responsible for this emission. But interesting thing is, as you can see at the top two panels from far UV and B band, this source that is potentially contributing to this mean infrared emission is not detected at all, but they only start to emerge in I band. And in the H band, finally, we can see their sources right there. And it looks like it's a source D region instead of source C region is responsible for this mean infrared emission. But issue is, if we zoom into this region, so this is HST H band, this region C and D breaks up into at least 10 clumps. So with Spitzer resolution, we could not tell which source is really responsible for this mean infrared far infrared emission. And in fact, if we just look at this, we will see this source D where the arrow pointing at, or later we call this D0, is the source actually emitting the mean infrared emission. So in order to find out what source is responsible for this far infrared emission or mean infrared emission, our JWST imaging observation has observed this region with the imaging as well. And again, this is based on EIS program 1328. And with mirror imaging, we have the subarray sub-128 mode because this is a very bright source where it will be saturating. And this is will be smaller, but it's large enough to cover this overlap region, as you can see in this gray box on the right-hand side. And then also overlap the MIPS 24 microns, so you can see this region is fully covered. And we have 5.6 microns, 7.7 micron, and 15 microns data using this imaging. And I shouldn't be surprised, but it always impressed me is the exposure time is less than a minute, and we got this beautiful data. So I want to show you the beautiful data, but I also want to show you how much improvement JWST actually provided. So I'm going to show you the region that I draw in the white box on the right-hand side here. And the corresponding region with the Spitzer data, it shows like this on the left-hand side. And then with JWST, this is what we found around at the same wavelengths. So earlier that was 5.8 micron, now it's 5.6 micron. So we get the resolution close to HST now, and we'll be able to study the details of the structures in mid-infrared, which is really impressive. Okay, so here's a direct comparison with the HST imagings. The middle panel is 0.43 micron, and the panel on the right is 1.6 micron. And mark the sources with plus and circle. So the one with plus, those are the HST detected sources, and the one with circles, those are JWST detected sources. And you can see on the JWST sources, there are some HST sources detected not shown in HST, not showing JWST. But interesting thing is there are sources showing circles, but without plus. Those are the sources that are detected in JWST, but not in HST. So in addition to this sources, this is very bright, but surrounding region, it seems they are also quite dust obscured, which we're not even seeing in the 1.6 micron around here. Okay, and so we only we don't only have 5.6 micron, but we also have 7.6 and 15 micron. So here are all the images we have so far taken for 2086. So let me mark them again. So source C is around here, and source D is in basically these two bright sources with this region around. So is region D, and finally region A at the bottom. And you can immediately find out which source is actually responsible for near-infrared and far-infrared emission by just looking at this. So you can see this source on the left-hand side, where we have ID number 8, is actually the one that's the dominant in the near-infrared emission. And its flux has been, its emission has been increasing with wavelengths. And it's at 5.6, 7.7, and 15 micron. At the 15 micron, it's so bright, it looks just like PSF. So when we looking at this, we know the source, earlier say I call it IDD, or from other paper, they call it ID1, ID8, sorry, I said ID8. And from the other paper, they call this source D1, so we also call it D1. This one very red unresolved source dominates the all near-infrared wavelengths. So the interesting thing here is this source is not the brightest source in H band. So this image is NICMOS 1.6 micron image. D1 is not as bright as D0. So if we only look at this and try to assign which infrared sources, if you might feel natural, D0 is the source dominant for near-infrared. But what we found with JWST is that's not true. So even source, they are brightest, they are not that bright in 1.6 micron, can be the dominant source in near-infrared. So this is what we found here with JWST. And if we try to make the color diagram, sorry, not color diagram, the color image, false color image is shown on the right-hand side. I use here blue is 0.4 micron, green is 1.6 micron, and red is 5.6 micron. First of all, it's just beautiful, but the interesting thing is the variety of colors seen in this disturbed region. For region A, the emission is dominated by optical, and region C is bright in 1.6 micron, which is also true for region D, but region D is dominant the near-infrared emission, so it shows a much redder color. And again, you can clearly see here, D1 is the single source that is responsible for most of the near-infrared emission. So then we will be curious about the color of all these sources in near-infrared. So we already know 2096 is the one of the reddest sources among all the local LIRGs. So we have done Spitzer synthetic photometry with the mirror filters shown on the left-hand side. So 4 spectra shown here are the 4 targets from ERS. And the filters here are the filter sets we use for mirroring. And we've done this synthetic photometry and made the color diagram shown on the right-hand side. X-axis is 770 divided by 560, y-axis 1500 divided by 560. And you can see 2096 is much redder than the crowd of 200 LIRGs that we have observed earlier with Spitzer with the GOALS project. And we already knew this, that 2096 is the red sources, but issue is because the slit of the Spitzer was large. So you can see we will not be able to tell the colors of the individual sources. But finally, with JWST, we'll be able to decompose the color of the 2096 to individual clumps. So
sorry, Hanae, just a quick question. Which of the apertures you showed corresponded to the red color?
Yeah, so it's a combination of 2, actually.
Okay.
Yeah, so the red one is covered all the way to 15 micron, and the blue one covered the shorter 2 wavelengths.
Okay.
Yeah. And so blue one is show low, and red one is long low.
Okay. So it's red even when you include just the blue component?
Yes, that's
okay. Wow.
All right.
Thanks.
Yeah. Okay, so here's the composition of only the single color now into the 12 clumps that we have detected. And the good thing is the sum of the Miri colors, they agree well with what we have observed earlier with Spitzer data. So the Spitzer and JWST data agree. And the interesting thing we found with JWST is most of sources say red. So you can see all these sources lie above the cloud of gold nuclei that was observed with Spitzer. And of course, source D1 or ID8, the source we have been interested in that is responsible for most of the infrared emission, is the reddest. Okay. And, sorry, I meant to show this. And you can see the location of each source in this diagram. On the there's smaller numbers at the bottom right, and the larger number goes to the top left. And there are sources, for example, like ID12, that's right, this one. This is not detecting optical, and ID3, this is also not detecting optical. Those are, again, the reddest sources. Okay. And then we will be curious what this D1 actually, how much energy has been generating. So with, for the quick answer, D1 actually generates up to 70% of the total LIR of the whole system. And the way we estimate this is we use the 3 different methods to get LIR, which we estimate to be about 5 times 10 to the 11 solar luminosity. And the 3 methods, first one is we assume the 15 micron emission correlate with the LIR emission. So we estimate the fractional contribution of each clump, and then assign that to use that to calculate the LIR for each clump. And we also use 15 micron volumetric corrections. So based on gold nuclei, which have similar colors as the 2396, we calculate the LIR over L15 over LIR, and use that to estimate the LIR based on the color of the clumps of each clumps. And finally, we use IR8, which was proposed by Airbus LTL 2011. And this correlation also gives us the LIR around 5 to 10 to the 11 solar luminosities. So good thing is all 3 these methods give us more or less the same LIR estimates. And the source size of this D1, it's as you can see, it's a PSF, so it's unresolved, and we will not be able to measure its exact size, but we can use a PSF size as the upper limit, which is 175 per sec. And based on these 2 measurements, we got the infrared luminosity surface density of this source to be 3 to 5 times 10 to the 12. And this agrees well with the VLA 33 gigahertz estimate by Song et al. 2022. And this high value is actually consistent with superstar clusters and ULIRG nuclei. So it's quite impressive, this one source. It's just almost it's off nuclear. We have to remember this. This is an off nuclear source, has very large infrared luminosity surface density. And then the next question we'll be curious is what would be where this source will lie again compared to Eddington limit. So there's the column density estimate from Wu et al. 2022. That's from ALMA CO observations, which estimate the molecular gas mass will be 2.5 times the 10 to the 9 solar mass also in their observing beam. And that will let us to see where this source lie compared to the Eddington limit. So here's the diagram I took from Pereira Santeria et al. 2021. And you can see from the number I showed earlier, our very high clump density actually lie outside of this diagram. So 2096 is actually, you can see it's quite dense, but this actually, we only have a limit. But if we use a limit, this one actually lies below the Eddington limit. But I mentioned the high density of this source, but it's not actually as high as up to 20. So they are actually even more extreme case compared with 2086. So we will not be able to tell if this this source D1 is self-sustained or not, but with a higher resolution data in the future, maybe we'll be able to see, actually measure the size of source D1. And then a question is, what is the energy source actually powering this source? So one useful tool is using pH emission, polycyclic aromatic hydrocarbon. So on the left-hand side, I'm showing the median SCD of the starburst dominant source and AGN dominant source that was made with gold. So about 200 of the gold sample, gold nuclei. And you immediately notice this pH emission is very strong and wide features. Is evident very strong in starburst sources, but in AGN, you don't see it very much. So they are the very good indication for star formation. So, and we actually observe this source with Spitzer and Akari as well and detect the PAH. But the issue is it's not strong enough to make us feel comfortable to say this is starburst dominant, but it's not weak enough to make us say this is AGN dominant. So we're hoping JWST will solve this issue for us. So with the imaging data, we can actually start working on this, try to investigate how strong this source have pH emission. So the three filters that we use is shown in green highlights here. You can see as a 770 filter nicely covers 7.7 filters, but the other two filters samples the continuum. So in the color diagram I showed you earlier, the x-axis, 770 divided by 560, it actually works very nicely as a 7.7 micron pH probe. And it actually nicely correlates with the 6.2 micron pH equivalent width as well. So 6.2 micron pH, this is in the gap here. We have this measurements from Spitzer data, and we color code our data points here with the pH equivalent width. And when in the Spitzer data, we often use 0.2 as a threshold to call AGN dominant source. And for star sources, when it's higher than 0.5 also, that's when we call them it's a dominant in the star formation. And you can see this color that of equivalent width actually correlate quite well with our probe here with the two bands color. And so up to here-ish is the AGN dominant, and we can comfortably say the sources beyond here is starburst sources. So if we plot the same diagram with the individual clumps that we finally detect with MIRI, both of the clusters, star clusters, or clumps, star-forming clumps, they lie in the starburst regime. But unfortunately, the source we're interested in, those D1, the one that we have been trying to find out if it's AGN or starburst, actually still stay in the middle range here. Don't give us the final answer if this galaxy, if this source is dominant by AGN or starburst. But let me put together all these indicators to see source D, the property of source D, and then we can think if this source is starburst or AGN. So like I mentioned, pH indicator is still at the border for this source to tell if this is AGN or starburst. But interesting thing is this is one of the reddest mean-infrared nuclei, mean-infrared sources. And this luminous surface, infrared luminosity surface density is comparable to LIRG nuclei. And I didn't mention this in my talk earlier, but the stellar mass estimate from H-band is about 10 to the 9th solar masses. And there's also speculation this source might be the potentially the third nucleus, and this diffuse emission we see around it could be the disk of remnant of the merger. And finally, X-ray spectra actually favor this source to be star formation. But the issue is it has a relatively high Coulomb density, like I discussed earlier, and so we cannot completely rule out compton-6 AGN. So all this list made me, I personally still very inconclusive to call this either AGN or starburst. So for example, the reddest being very red could be the good indication of AGN. But what interesting thing we found with JWST is these red sources may be quite common. And so this is VB114, another target from our ERS program. We have detected many red star-forming clumps up here, which is as red as this source D. So being red is in this 1500 and 506, 15 micron over 5.6 micron in this regime may not be enough to just claim this source is AGN. And so I personally still think it's inconclusive to call this AGN. I still believe this source could be starburst. So we will need to wait more data from JWST to do this. That I mentioned earlier, we also are waiting for near-spec MIRI IFU data. If AGN, I would expect we'll have coronal line detections because only AGN can produce them. And then also in that case, I will see the lack of pH emission because this pH emission can be destroyed in a harsh radiation environment due to AGN. But for starburst, I expect the opposite. But I also learned recently there's a complication for detecting coronal lines. So this is work by Vivian Yu for Mercury 273. We know there are two AGNs as in this galaxy, but the nose one being compton-6 might be make it hard for the coronal line to be detected. So you can see this diagram, it's just a flux map for coronal line SI6 on the right-hand side. The southern source have a detection, but northern source has no detection. So maybe pH could be more reliable diagnostics. So this is the earlier work used Akari data and Spitzer data. And y-axis is 3.3 micron pH equivalent with. So when it's stronger, people think it's when it's a higher value, people think it's a starburst dominant. And x-axis is the color at 4 to 3 micron, also 4 to 2.8 micron. And when it's redder, you can see it's likely to be AGN dominant. So this is basically this region you can see with this increasing very steep slope as heating by hot dust can be due to AGN. And if it's a missing pH emission, we will be confident that this source is likely to be AGN dominant. But not only, this is not the only thing that will be interesting for 2Z86, not only the diagnostics, but we'll be able to do a lot of studies to study the properties of this source. So in this wavelength range of near-spec and MIRI, we'll have many ionized atomic traces to study ionizing structure, density, and so on. And the suite of warm molecular gas, H2, will also let us study the temperature, mass, and if there's a shocks in the region. So this actually has been already done by our team for other galaxies. This one, you can see that we study the dust properties against radiation field using neon 3 over neon 2. And Vivian here also have done the work studying the shock traces by using H2 against iron line. Okay, so I would like everyone to stay tuned. So in a few weeks, we hope we'll be able to give you the answer if the source is powered by AGN or starburst. So here's a quick summary of my talk. So we finally, with JWST, we have spatially resolved the near-infrared emission of the merger-induced dusty region of 2Z96 shown on the right, shown this image. This is HST image. And with Spitzer, this is what we got. But now what we got is like this. And here we have the 12 near-infrared clumps detected via new sources. And most of them are redder than the local LIRGs nuclei. And the source that dominate the near-infrared emission is the source we call D1, or we call it ID8. And that is accounting for up to 70% of LIR. And its infrared surface density we only get the limit because we don't have the exact size measurement, but it's still below the limit if we assume the PSF being the size of the source. And unfortunately, we're still inconclusive for the compton-6 AGN or starburst for this source, but please stay tuned because the upcoming JWST should be able to tell us the final answer. Thank you.
Thank you, Hanae. Thanks for a really nice talk. I'll add that, the source of D1 is definitely brought up a lot of animated discussions within our group, but we respect your inconclusiveness about this. Do we have questions from anyone in the audience? Stephanie?
Yes. Hi, Hanae. Good to see you.
Good to see you.
Nice, very nice talk. That was very fascinating. I guess I would probably be in the AGN team, but I just wait and see and hope. But I had a question about, because you mentioned these kind of complicated, well, the geometry seems to be a bit complex, but also like the kinematics. Are there any arguments you can make from maybe coming from simulations of like how this would work if it would be a third nucleus, I guess, compared to the two other nuclei? Like would that be likely to be the center of a galaxy? And in this case, perhaps there's both an AGN and a bit of starburst like around it. But
yeah, so far in the past, we have the teammate who have tried to do this with a simulation, try to reproduce if this is a 2 or 3 stage merger using like H1 data and so on. But so far we don't have anything. But what we expect with JWST is, since we will have IFU, we can study the kinematics around the source. So if there is a rotating feature around this source D or D1, then that might be a strong evidence this is actually a remnant of a disk galaxy that merging into this. So that could be the indication this source is the third nucleus.
Yeah. Okay, very interesting. Thank you.
So hopefully in a few weeks we'll know that.
All right, I'll stay tuned. Thank you.
Thank you.
Claire? Oh, you're muted.
I was going to ask the same question to Stephanie, but I wondered, are there examples in GOES or elsewhere where the nucleus is both? So it's an AGN surrounded by intense starburst that is so tightly compact that you can't see separate structures.
Yeah, I guess it's possible. It's possible. So yeah, so I think you are not asking about like AGN at the center and then star formation ring around it. You're thinking it's much, we can, at this level, we cannot resolve, I guess. Yeah, it's possible, but with the current relation, we cannot tell. And but with the 4 targets we have, maybe if we haven't, sorry, let me see if I can get back easily to 4 targets. Yeah, so we don't know, I should say, at this point. And but at least for NGC 7469, we have the spectra of the center, right at the center here. We don't see any PAH emission there. So if any, it will be very weak. So I think at least NGC 7469, right at the center with the nucleus, I think it's probably likely pure AGN. But for the other sources, we have to look into them more carefully. But for BB114, that's an interesting case. Eastern nuclei actually, this is in the Aaron Evans paper. It's actually 2 cores we have seen. And we still try to find out if any of these, one of them are AGN or not. Yeah, so but that's actually physically separated. We can resolve them.
Thank you.
Thank you.
Yeah, and I guess I'm adding to Claire's point. I guess, I don't know what kind of physical size scale it would have to be, but if you have starburst kind of on top of each other, very, very close age, unless it's projected, otherwise, I imagine that the molecular clouds is going to be destroyed by the AGN ionization radiation. So unless we're talking about a projected case where we're seeing a long line of sight, some star formation just sitting on top of the AGN, but otherwise, maybe within the resolution of everything that we've seen so far, I don't think we've seen cases of what you're talking about.
Well, there's the third dimension, right? The star formation could be between us and the AGN.
Exactly. So yeah, it could be projected. Yeah. Actually, Stephanie?
Yeah, just continuing on this, I think in NGC 7582, what we see is a mixed contribution, but it's also a ring, a larger ring, maybe similar to 7469 that you have there. But the ring is more sideways. So I think we see some of the starbursts in the ring in front, and then the AGN. And I think there might be a gap between, but it's just along the line of sight. But again, we have to speculate too. We not have the full resolution to know for sure. But I was going to say 7469 looks much more orderly in the center. So it wouldn't be surprised. And maybe the ring is a bit more inclined. So we have a view there of the central AGN, and the others are such more train wrecks that it could be. So I was going to ask maybe a follow-up if you already have looked, or if it's possible to look in the radio to see if there's any radio point source or jets or something.
Yeah, for 2086, yes, there are actually jets detected. Was it 2086? Sorry, maybe it's different source, but we have radio observations. And 2086, like I mentioned earlier, we have 33 gigahertz observations, and this source D1 actually is detected. And so far, all the measurements are consistent. And for the jet, maybe I remember wrong. The jet was from another target. I think it was NGC 3256, but 2086, probably not.
Okay, because I guess what people do sometimes in radio is if you have different frequencies, you can check if the spectral index, because it could be unresolved, and you can check if it's more. But what we saw also is we had this in-between case where it could be starburst or a jet. So yeah, it's not always obvious even with radio.
Hanae, could you remind me when you said that the size of the source is what, 175? It's smaller than a PSF. What band is the PSF? Are you talking about? Is it 15 micron or?
Yes, it's a 15 micron.
How does that compare to the radio source size?
Radio is actually slightly smaller, I believe. And sorry, I don't have the number here.
Okay, sorry.
But I think it's smaller. It is smaller. Yeah, I don't have it here. Yeah.
But let me actually ask a follow-up question. So I know in your plot that you were showing, in terms of the AGN and the starburst diagnostic, your C1 source or C0 source was, I know you didn't focus on it here, but it was kind of on the AGN side. Do you think that could potentially be? Sorry,
I know.
Yes, Team AGN,
I know.
but
I agree with that. Actually puzzled me too. So it would be. Yeah, I think you are talking about this one, right? At the bottom.
Yeah, exactly.
Left.
Your Z0.
Yeah. Yes. No, this is a weird one. And let me put this together. So that's number 11 is up there. So it's quite, I don't know, to be honest, because also it's it's quite diffuse as well at the near-infrared emission. This shows you can. Sorry, it's hard to see it, but you can see my cursor. It's this one.
So it's compact at 1.6 in the NICMOS image, but it's diffuse in the longer wavelengths.
To my eyes, look a bit diffuse, but we have a deeper imaging data from full array. So I think we should look at those, because those are deeper than the mean for, with the subarray, deeper than subarray. And the issue is it's saturated, so hopefully it will not affect this region badly.
Okay. Yeah, sorry, I didn't mean to monopolize the questioning. Shavita, you have a question?
Oh yeah. First, excellent talk, Hanae, and just beautiful data. So thank you so much for sharing it. So I wanted to just ask a question about just star formation in general, because apart from the AGN question, is there anything from the JWST data that you can get that that you didn't have in the Spitzer data on constraining, say, the IMF, because these are tremendous star formation rates, right? And you have so many different clumps here that you can now resolve. So I wondered, is there, plans and some definitive thing you can say about, the star formation rate, the IMF, are these required to have top-heavy IMFs? I'm not sure where things stand with that issue.
Yeah, so amazing thing is, like I mentioned earlier, that so in this range, you have more sensitivity and more spatial resolution and more spectral resolving power. So increase of sensitivity give us will detect the faint lines we couldn't detect before. For example, I was really excited to see hydrogen recombination lines in the data in the near infrared and mid infrared. So that is will be the excellent lines for estimating star formation rate. And also we can do suddenly I forget the word, the extinction measurements using the emission lines. And so I'm actually excited to do that kind of things. And thanks to the high sensitivity and the spatial resolution, well, like you mentioned already, we'll be able to do this for individual clumps. And the spectral resolution power will start to let us to see the profile of the emission lines. So one work I have done with Spitzer data was the high-res. It was only R600, but now we have R3000. So we can see how use the line profile, the line shift, and then see the kinematics of the sources. So, and we finally to see is how much inflow, outflow, and such of in around the nuclei of these local LIRGs. Yeah, and lots of lines, like, it's later in the slides. For example, give us to do some metallicity measurements, ionization measurements. The important thing is these are all in infrared, so we don't need to worry about dust extinction. So, and that'll be maybe exciting to compare with optical results and then see how well they agree or not agree.
I saw a couple of hands up earlier, just wondering if Enrique or Stephanie, do you have any questions you want to squeeze in? We have maybe a couple more minutes.
Well, I guess it's maybe a short one. And maybe you said this already, I don't know if I missed it. When you were showing, it looks like D0, D1, or 7 and 8, like are those like a double, like possibly a double source? And I guess will the IFU cover both and you can tell if there's kind of two and the kinematics and all that? Okay.
Yeah, so D1 and D0 are right next to each other. So yes, they will be covered together.
Because I was wondering if one is a starburst and one is, well, I don't know, who knows?
It's possible.
But, I mean,
both are starbursts.
Well, okay, perhaps.
Sorry,
but no, I mean, it could well be. I'm just, you know, I'm just very intrigued. Maybe you'll see me show up in your office the day you get your data.
Chris? I think we can't hear you. Even though you're not muted. I don't know if it's a microphone input issue. Oh,
can you hear me now?
Yes,
yeah.
Yes.
I was wondering if how the star formation history might play a role in the infrared emission. Like, is it possible if there's a population of built up old stars that are seeing new dust as part of the merger and making this redder than we might expect? Or?
Oh, well, okay. So all star, I think in infrared, that would be a bit tough because they are not hot enough to make this very steep red color that we see in here. So I don't think all star will be able to do that. But thinking about the star formation history would be interesting to see what kind of populations actually, if it's a starburst, what kind of population and in such a what kind of such short time it can actually produce so much hot emissions and to make the color this red. Yeah.
Okay, that makes sense.
Yeah, especially it's unusual, right? It's outlier. If I show you the color. Sorry, I have too many animations. It's a bit slow to go ahead. Yeah, here you can see it's much redder than any other nuclei. Yeah.
Yeah, it's very strange.
Yeah, it is. Yeah.
So Enrique actually had a question about the radio masers, and then he found his
yes,
answer.
That's right. Sorry, I didn't mention that in the talk, but yes, there is a maser detection. Yes, and at the location of D1. Yes, and that could be. Oh yes, there is. I think this had a couple of masers. Am I right? I cannot remember really well, but there is at least one maser. It's very, very dense. Okay, well, I think we're up at the hour. So thank you, Hanae, for the really nice talk, and I really appreciate the discussions from everybody. Afterwards, very interesting. Shobita, did you have any announcements you want to make?
Well, Hanae, our students.
I have one.
Okay.
Yeah, I'm gonna post a Zoom link in the chat for the student discussion afterward. There it is. And I think our speaker can make it. So any students who want to join that, there's the link. And I think the link is also in the Discord for the students in the Discord. Yeah.
Great, thank you, Jeffrey.
Yeah.
And I emailed you the link, Hanae, as well.
Oh, thank you. That's really helpful. Thank you.
It should be in your inbox.
Yeah.
Okay. And Shobita, did you have anything else? If not, then I guess we'll thank Hanae again, and we'll see everyone else in a couple of weeks. Whenever that next AGN seminar is, I should just let Shobita send out the announcement. I shouldn't make up dates.
Thanks, everyone. See you in 2 weeks.
Thank you.
Thank you very much. Bye-bye.
Bye.